Hi everyone, welcome to this machine learning and MFG game seminar. So today we're very happy to have Niao He, who is joining from ETH Zurich, from the Optimization and Decision Intelligence Group. So today Niao is going to talk about policy mirror assent for efficient and independent learning in MFG games. Thank you very much, Niao, for accepting the invitation and for giving this presentation. And well, the floor is yours.
All right. Yeah. Thank you, Matthew, and thanks for the invitation, and thanks for having me. And also many thanks for the organizers for running this very timely and exciting seminar on MFG games, and also keeping it live even after pandemic. That's not always easy, I'd say. So I'm very happy to discuss some of our very recent work on this line, like using policy mirror descent for solving MFG games. And I have to admit that this is also my first project on MFG games. Since we started to explore into this area like last year, and I have to also admit that most of the things that I've learned about MFG games really come from this seminar theories. So many thanks for that. And that being said, I'm sure many of you are more experts on this topic than me. So please feel free to interact with me if you have any questions or if there's anything that's not clear to you during the talk. So first of all, I'd like to say that this is joint work with Batu Yardin, who is a second-year PhD student in my group at ETH Zurich, and this work is mostly driven by him, I would say, and also with Sami Kaitzi from, he's now an assistant professor at the RWTH Aachen in Germany, and also with Matthew Geist from Google Brain, which I'm sure all of you know by now. And the link of the paper is also on arXiv, which you can check it out afterwards if you're interested in more details. All right, so let me start by really just highlighting or reminding you about many of the great successes we have witnessed about reinforcement learning in the past years. I'm sure some of these are already probably overshadowed by the craze of large language models these days. But anyhow, we have seen a lot of successes in achieving really superhuman performance in many challenging, complex tasks by reinforcement learning in video games, board games, and also the success has now expanded into more scientific domains, like in designing or new novel matrix multiplication, in numerical like computation, or in automatic plasma control for nuclear fusion and many others. And curious, I think it's hard to predict what will happen next, but what's probably easier to predict is kind of the growing synergies between optimization and reinforcement learning. As we move from single agent settings to two agents to potentially finite many or infinite many agents. As we have seen that optimization provides not only a rich tool to model all kinds of different decision-making problems when we have a multi-agent systems, such as using policy optimization for the single agent reinforcement learning setting, or using minimax optimization for two-player zero-sum Markov games, or the use of like decentralized optimization or equilibrium optimization to deal with multi-agent systems with competing agents or cooperative agents. And optimization also provides a lot of algorithmic tools and theories for us to understand how reinforcement learning algorithm works. And in particular, I would say we have seen a lot of tremendous empirical successes with policy gradient methods, which are first-order optimization algorithms in practice, both for single-agent reinforcement learning and also for multi-agent reinforcement learning systems. And more lately, we have seen a significant line of research, particularly theoretical progress, where we have much better understanding of the performance of policy gradient methods, particularly their convergence to global solutions in many important settings, such as single-agent reinforcement learning, zero-sum Markov games, or Markov potential games. Right here, I just list a very small sample of literature or papers on this topic. And as I said, this is a very fast kind of growing field, and the literature are kind of growing exponentially these days. So I'm sure you will see many, many more papers coming out on this topic. So a natural question here we wanted to ask is really how far can we kind of push the boundaries in terms of understanding or using policy optimization for multi-agent reinforcement learning. And we know that in general, right, multi-agent reinforcement learning is very challenging to solve, and there are already many hardness of results about the computational complexity of these problems, and also a lot of negative results about non-convergence policy gradient methods for multi-agent systems in general, or even for general Markov games. And it always makes sense. I think a reasonable objective here is really trying to consider more structured games so that we can hope to get some sort of theoretical guarantees out from it. And in this talk, we're going to focus on a special class of kind of games, particularly finite player games with symmetric and anonymous agents. And by symmetric here, I really mean that the underlying transition dynamics and also reward for each agent is sort of symmetric. And by anonymous here, really mean that the kind of the impact of multi-agent interactions here on your transitions or reward is really purely through the state distributions of all agents as a whole, rather than like each individual agents or the joint actions. So there are, of course, a lot of applications that can be framed into such type of games, right? We have already seen tons of applications that were discussed in this seminar theories, like in auctions, in cloud resource management, in transportation, so on and so forth. I'm not going to many of these details here. I'm sure you can watch the recordings of previous talks. And here, particularly, I just want to give you the example of this basic commuting between two different cities, where you can basically treat all these cars as anonymous kind of agents, and the travel time that they need to spend when taking a particular route is really determined by not only this particular route, right, but also depends on kind of the distribution of all cars over different travel routes here. And what's particularly interesting, or the most kind of profound structure here, is really that if you think about the case when the number of agents goes to infinity, then this sort of reduces to the so-called stationary mean field games. And this greatly simplified a lot of the mathematics and also the algorithm designs underlying. And again, this has been extensively studied and discussed in many of the previous seminars in these theories. And in this talk, I'm going to just give you a very brief refresher of these connections between M-player games and mean field games, so to make sure that everyone is on the same page. And let me just be more specific about the problem setting that we're looking at here. We're looking at, basically, we're interested in M-player games with homogeneous agents, and we're going to consider particular finite state action spaces, S and A. And as I said here, the transitions and rewards in these games is going to be only going to depend on the state distribution and also the actions that each individual agent takes. So more specifically, at every time t, a player I basically observes some state STI, and then it will decide to play some actions AI. I denotes the different agent I, and T is the timestamp here. And this will trigger a transition to a new state, ST+1, for agent I, and that will follow this dynamic P, which will solely depends on the current state of agent I, the action that agent I takes, and also the empirical state distribution mu hat T here. And similarly, the agent will receive a reward, which only depends on the current state S of the agent I and the action it takes, and also the empirical state distribution mu hat. And we know that this mu hat basically follows the discrete time Fokker-Planck equations. So the goal here for each agent is then to try to maximize their own regularized discounted total reward. Here I'm going to consider some regularization parameter or regularization terms H into the objective, and I will discuss a bit more later, like why we consider such a regularization h here. For now, we just treat this as any general arbitrary function h, which can also be equal to 0. And for each agent I, their value function now I'm going to denote as j of I, right? This value function is going to depend on this regularization h. Of course, it's also going to depend on what is the joint policies pi of all agent that all agent take. And also it depends on this initial distribution mu0 that the system starts with. And in the finite agent settings here, a notion of solution would be the so-called Nash equilibrium. So in this case, we can define the Nash equilibrium as a policy pi such that no agent has any incentive to deviate unilaterally from this policy pi, right? In other words, right, you can view that if each of these other agents stick to the policy pi, then this policy for agent I, pi I, is going to be the best response of this underlying system. And particularly here, we're going to consider just the delta Nash equilibrium, which is an approximate Nash equilibrium, which basically says that the agent cannot exploit more than delta from other agents if they change their policies. So this is kind of the basic notation of the solution here for n-player games. And as we said, as n goes to infinity, if you have infinite number of agents, then this basically can reduce this to a representative agent plays against the whole population. And in this case, we can consider the notion of stationary mean field games, where we can define the value functions of a representative policy pi against the whole population mu, and we'll assume, say, this population mu is going to be fixed throughout the process, right? It is going to be fixed for in the probability transition dynamics and also in your reward here. So we can define the so-called stationary mean field Nash equilibrium, which is basically going to be this pair of solutions pi star and mu star, such that the pi, if you are going to fix this population mu to be mu star, then pi star, this policy pi star, is going to be the optimal policy with respect to the underlying system. And if you're going to fix your policy to be pi star, then this mu star is going to be consistent. And it basically follows this stability condition here. So basically, a Nash equilibrium has to satisfy both the stability condition and the optimality condition. And an important note here, as already been discussed many times, and also a very profound observation, is that the solution or the stationary mean field Nash equilibrium can be used to approximate, or can actually lead to an approximate Nash equilibrium for the n-player games, as long as n is very large. Particularly, this basically implies that if you have a very large system with many agents, then basically there's no cost, or the cost of considering basically just a mean field Nash equilibrium is very low. So this is kind of the reason that motivated a lot of research interest and also work on how we can actually solve mean field games and try to use reinforcement learning techniques to solve mean field games. And I'm going to just basically give you just a very brief kind of summary of some of the work that has also been discussed earlier in this seminar, right? So there are various algorithms that has been studied of how you can use reinforcement learning to solve stationary mean field games. There are algorithms like Q-learning or fitted Q-learning algorithms, policy gradient methods, fictitious play, etc. And particularly many of these algorithms, we note that they oftentimes need to make a very underlying assumption that the composition between of your best response operator and the population update operator has to be a contraction, or has to be a contractive mapping. And this is oftentimes used not only in the proofs, but also is used to also kind of as a way to design the algorithms as well. And lately, I think in the recent work by Anna Hitachi et al. And co-authors, they've shown that in general, if you add a regularization, particular strongly concave regularization in your objective, then the corresponding regularized best response operator indeed satisfying these contraction properties. So besides stationary mean field games, there have been also tons of other work that look at other, mean field games like finite horizon mean field games. And many algorithms has been studied in this domain as well, like fictitious play, online mirror descent, etc. And this work oftentimes also needed to make some structural assumptions like the monotonicity on the transitions or on the reward functions, or sometimes they would even also need to assume that the transitions may not necessarily depend on the underlying population. So there are also other works that look at more specific settings like linear quadratic mean field games. So while we look at many of these recent work, we noticed that there are a couple of kind of limitations with many of these results. The first limitation we observe is that many of these algorithms, as I mentioned, require this very strong blanket contraction assumption about the best response operators. And it can be shown that, in fact, even proving Lipschitz continuity of this best response operator is not necessarily trivial. Or in other words, we've shown that the Lipschitz continuity really only holds in trivial settings where the best response under different populations is the same. And that means these assumptions might be in general just too strong to assume. So this similar observations has also been studied and observed in this other paper as well. So a natural question here is, can we get rid of these kind of very strong contraction assumptions? So the other limitation is really that many of these work rely on very kind of abstract or unrealistic oracles. And these oracles assumes basically that you can simulate these mean field games. Basically, you can assume that you can simulate infinitely many agents in order to manipulate on the population distribution mu and to run your algorithm. In some of this work, they also needed to basically require some generative models where you can generate any sample action pairs from any given input SNA or your population mu. So in practice, oftentimes such a generative model may not always exist, but what you have is really just some online samples or some offline data that you can get. So as I mentioned earlier, also that many of these algorithms require computing best response at every iteration. This basically reduces this to solving a full single agent reinforcement learning, which can be very expensive. And lastly, but also most importantly, I would say that most of this work assumes implicitly that there is a centralized controller that can coordinate among all agents so that they will be able to deploy the same policy at the same time in order to mimic the mean field games. So in this work, we try to really hope to directly solve these M-player games without having to without having to resort into a mean field game simulator. Particularly, we're interested in designing algorithms that only leverages this N-agent simulator and only leverages just a single pass samples from a single sample pass from this N-agent simulator by interacting with the environment. And we don't want to have algorithms that we needed to manipulate with the population distribution, because once the N agent is fixed, right, the population itself will evolve over time automatically. And particularly, we wanted to design algorithms that may not necessarily need a centralized controller, so that actually we can have independent learning among all of these N agents, and they can deploy different policies as they go along. So here's basically a brief kind of comparison between our work compared to some of the existing literature on these learning mean field games or M-player games. And let me just start by giving you a high-level idea of our algorithm, and then I will go into a bit of more details on how we designed the algorithms and how we did the theoretical analysis. And the goal, as I said here, is really we want to just simulate an agent gains and learn from these samples to find the approximate Nash equilibrium. And here we assume that the algorithm cannot modify the underlying population mu or the empirical state distribution mu hat, right? The only thing that we can really manipulate with the algorithm or with the agent is just the policies that they deploy. So the main idea of the algorithm is really follows many of these similar ideas that in the single agent reinforcement learning, which is kind of like an actor critique type of algorithm, right? The idea is at every iteration, like each agent, they're going to fix their policies, and then they're going to perform some TD learning type of algorithms in order to estimate what is the current Q values. And then once we obtain some Q value estimations, we're going to use it to perform some policy mirror ascent update for each individual agent. And they're going to perform this update simultaneously in parallel. So the policy mirror ascent step here is basically where you, for given Q value functions, you look at this something like basically a mirror ascent step where you use some Bregman divergence to help you guide the policy update. And particularly in our analysis, we are going to focus on just using Euclidean distance here. The analysis or the algorithms might be generalizable to also other Bregman divergence as well. As I said, this kind of framework is also widely explored in single agent reinforcement learning setting. And this is particularly motivated, I would say, by the work by George Lam policy mirror descent for single agent reinforcement learning. So to be more specific, how the algorithm works is basically as follows. So here are the algorithms for the centralized setting and also for the independent learning setting. So for the centralized learning setting, we're going to so there are essentially just two key steps. One is the conditional TD learning step in the inner loop that we run to get an approximate and good estimate of the Q value functions. And on the outer loop, we're going to just run the policy mirror ascent step. And in the centralized setting, we're going to have a centralized controller that is going to broadcast this policy pi to every agent. So every agent is going to use the same policy pi to generate the data, generate a sample pass for them to estimate the Q value functions. So here, when we update the Q value functions, we're going to just pick any representative agency, just agent one. We're going to use the sample pass it generated, and then we're going to use it to update the Q values based on some TD learning scheme. And in the independent learning setting, what we do is we're not going to have any centralized controller here. So instead, every agent might deploy their own policies pi I. And every agent is going to learn to estimate what is the Q value functions, Qi, right, based on the sample pass they generate. So basically, we're going to update the Q values and pi and policies independently for every agent I at every iteration. So these are basically how the algorithm looks like. And before I move into kind of our theoretical results, let me just maybe pause a bit here to see if there are any questions from the audience.
Actually, I have one quick question, maybe. So it seems that intuitively the centralized one makes a somehow stronger assumption. Is it more efficient, or does it have, like, I don't know, do you know if the centralized one is more efficient in some sense than the decentralized one or the independent one, or more stable or maybe less stable? I don't know.
That's a very good question and a very good observation as well, because the centralized controller, because it requires this centralization here, right? So basically that means you are requiring more information here, and it's more efficient because all agents naturally they should behave more symmetrically, right? So by enforcing this synchronization between the policies, you can imagine or you can expect this would give you better sample efficiencies. Whereas in the independent learning setting, right, agents might deviate from, they might use completely different policies, right? So it could means that it will take more time for the agents to actually be able to learn to achieve the equilibrium in the end. So I will go into a bit of more details in terms of like exactly what are the kind of theoretical guarantees that we can say about the centralized and also the independent learning settings, so that you can see that there is indeed a discrepancy there.
Okay, thank you.
Good. All right. So before I go to the theoretical analysis, I wanted to first also be crystally clear about what are the assumptions we make, right? So there are a number of assumptions that we make. So the first assumption is more on the Lipschitz continuity side of the operators that we study. So the first one is assumption here is very mild and also very standard. It's basically to say that the transition dynamics and also the reward are Lipschitz in terms of the population mu and the state actions. Okay. So the second assumption is also quite standard, which is to say that if you look at the per step population evolution, right, this has to be also Lipschitz continuous. In particular, we assume the Lipschitz constant is less than 1, so that this would ensure that in the end the dynamics is actually going to be very stable. Again, these are basically minimal conditions that you would need, even if you wanted to guarantee the existence of Nash equilibriums. And the third assumption is the one that is the most critical one, which is we are going to assume that there is sufficient regularization in the objective. Here we assume that the regularization H is going to be rho strongly concave in terms of the L1 norm. And also we assume that this strong concavity parameter rho is going to be sufficiently large, and I will specify later like exactly how large this rho needs to be in order for the theory to work out. As I mentioned earlier that in general, if you don't put any regularization at all in your objective, right, if you just look at the unregularized mean field game or finite player games, this is not very clear that first of all, whether you would be able to still build many of these contraction properties as you want. And as we mentioned earlier, that this contraction of at least best response type operators basically simply reduced to trivial settings. So it seems like some sort of regularization is necessary here. And particularly in this case, with these three assumptions, 1, 2, 3, we're able to guarantee that the corresponding policy mirror descent operator that we use will have this contraction property. And this is slightly different from many of the existing work, which assumes contraction properties more for the best response operator rather than the policy mirror descent operator. So the second set of assumptions, which is really needed because the fact that we're using only single sample paths to generate the data, so we needed to ensure enough exploration from this data. So the first assumption one of the assumptions we make is to trying to ensure sufficient exploration for all the policies we see during the training. So particularly here, we assume that the initial distribution pi is able to visit any action with non-zero probabilities, right? Also, any other policies that we use during the training is able to visit any state, visit any action with non-zero probabilities at any state. So these again are kind of very standard in the literature, and particularly it's worth mentioning that I think even in the single agent reinforcement learning setting, people have shown that with certain algorithms, like say for instance, natural policy gradients, or if you add certain regularization, like entropy regularizations, then you can actually guarantee sufficient exploration of your iterates, the policies you deployed during your algorithms, right? So this is less of an assumption, but rather of a property, depending on different algorithms or regularization you impose into your problem. So the second assumption, again, which is also very standard, is just to assume that there is sufficient mixing of your Markov chain. And particularly here, this basically ensures that you are able to visit every state infinitely often, eventually. So as I said, these are kind of very standard assumptions that, or different variations of these has been deployed in different papers, and more or less, I think the idea is to guarantee that you are able to visit every state and every action infinitely often, right? So that you can actually really benefit from this single sample pass. So here is going to be our main result, right? The first result is about the centralized learning setting, where we've shown that if we're going to use large enough step size eta, and if the number of outer loops, we use like basically the number of policy mirror distance steps if is of order log 1/epsilon, and the number of conditional TD learning updates we deploy in the inner loop is of order 1/epsilon2, then we're able to show that this algorithm is able to converge to the policy pi star, which is the Nash equilibrium of your mean field games, up to an error of epsilon plus of order 1/√n. Right? As I said, in this centralized algorithm, here we only use one single pass only use the sample pass from one agent to update a central policy. And then the central controller is going to broadcast this policy to every agent. And I wanted to mention also here that the abstraction of mean field games is really just using the proof technique, not really in the algorithm design, right? The algorithm really just run this n agent simulator to update their own policies. And what this result says here is really that this algorithm is able to converge to an approximate Nash equilibrium for the regularized game using just 1/epsilon2 total number of samples, up to the accuracy, which is kind of intrinsically, which is kind of the approximation error, because you only have infinite agents here. So this is kind of the one of the results we have with the centralized learning setting. As you can see that the total sample complexity basically matches with what we typically see also with single agent reinforcement learning. I should also mention that because that the mean field game Nash equilibrium is also only an approximate Nash equilibrium of the finite agent games, right? So there is an additional error like 1/√n, which is derived, or which comes from the fact that we only have a finite number of agents. So this is the same order as this other term here. So basically, based on this, you can also derive that similar upper bound holds for convergence to the Nash equilibrium of the original finite agent game. So for the independent,
yes. Can I ask you a quick question? Sorry. So yes, I was about to ask, but I think you just answered to that. So pi star here is really the mean field game Nash equilibrium policy. Okay, it's not the n player. It's not some n player game. Okay.
Right. So pi star here is the Nash equilibrium of the mean field games, and and you can translate this result to also the convergence to the n-player games, because we know that the difference between the n-player game Nash equilibrium and the mean field game Nash equilibrium is also of this same order.
And so somehow this big O here of 1/√n is kind of incompressible, in the sense that you make anyway some error. How can I say? If you try to approximate the mean field Nash equilibrium using only some population of size n, I think you are going to make some kind of incompressible error because you are not in the mean field regime. But if you were trying to approximate directly the n-player Nash equilibrium, maybe you could get it without this 1/√n, right? Because if you try to approximate the mean field and then you say mean field is close to n, you are kind of losing 2 times something that maybe you could save if you were trying to learn directly the n-player one.
Right. Yeah, that's a very good point. Indeed, yes. I think if you directly solving an n-player game without having to relate it to mean field game at all, maybe you don't necessarily have to suffer from this 1/square root and approximation error here, as you said. And I guess the kind of the insight here is more like if n is large enough, then you don't care about this. But of course, if n is small, then I think it probably does not make too much sense to actually relate it to mean field games. And yeah, and you're absolutely right. Yeah. Mm-hmm.
Okay, thanks.
Okay, good. And for independent learning, so the results are more or less similar. So what we can show is that if you use large enough step size eta, and again use logarithmic 1/epsilon number of policy mirror descent steps in the outer loop, and you needed to use a bit of more samples per iteration for the TD learning algorithm in order to get a good estimate for the Q value functions. And if you use slightly increased sample complexity here in your TD learning step, then you are able to achieve the same convergence guarantees as before, that you are able to converge to the Nash equilibrium of your mean field games up to this error here, which is similar, which is similar as before, right? Here, I should mention that this constant C here in your sample complexity or the number of iterations in your inner loop, this is a constant that depends on many of the problem parameters like the Lipschitz constants and also the strong concavity of your regularization parameter and also the step size you choose. And let me elaborate a bit here that as you can see that this means that you have slightly worse sample complexity than the centralized setting, which I think as we discussed earlier, this is more or less understandable because agents are deploying different policies, right? Unlike the centralized learning setting. And this means that if there is large deviations between these policies, then if you wanted to have really good, good convergence, you need to make sure that there is more and more accurate estimations of your Q value functions, right? So you need to pay a bit of more actual samples in order to have good estimation of your Q values to compensate on the deviation of the policies. And what's interesting though is that one can show that if the underlying dynamics is sufficiently smooth in the sense that, let's say, your regularization parameter rho is very large, the Lipschitz constants, like in terms of your action or L mu, which is the Lipschitz of your transition dynamics in terms of your population mu, right? This is basically to say, like, if this Lipschitz constant is very small, meaning that the impact of this dynamic, the population has a smaller role in your transition dynamics P, then in these cases, one can show that in these seeds just equal to 0, right? You can actually achieve this 1/epsilon2 sample complexity, which matches with the centralized learning setting. So with the remaining time, I wanted to just give you a quick kind of just an overview of the theoretical analysis so that you can see what are the fundamental differences of this compared to single agent reinforcement learning setting, and also the difference compared to a mean field games setting. So here in the theoretical analysis, there are literally just the two key steps. One is to show that this policy mirror ascent-based operator is going to be a contraction. And in fact, the mean field game Nash equilibrium is also a fixed point to this operator. So that this basically implies if you apply iteratively this fixed point iteration, assuming that you know exactly all the information about your policy evaluation, then this will actually converge linearly to the Nash equilibrium. This explains why in the outer loop, we only need logarithmic 1/epsilon number of iterations. So the second step is really trying to establish that for the TD learning step, when we try to estimate the Q value functions, this will need only like of order epsilon -2 number of samples if you wanted to have a good estimation on the Q functions against the mean field. Right here, the estimation error or the bias really comes from several resources. So the first one is really coming from the fact that we're using an agent simulator rather than the mean field simulator. Hence, there is a deviation between the empirical state population distribution versus the mean field. So this is sort of different from the mean field game setting. And then the other kind of bias comes from the fact that we're using a simple pass, single sample pass, right? And this is not just IID setting, right? So we needed to take care of this mixing time of the Markov chain. And the last bias comes from the fact that we're using independent learning. In this setting, then policies are different, so there is actual error comes to play. And to be more specific, right, so here's basically the definition of a bunch of operators that we used to construct our policy mirror ascent operator. So the first operator here we define as just gamma population, which is basically describes how the one-step population evolves, or how the population distribution mu evolves in one iteration for fixed policy pi. And if you do this, repeat this for infinite number of times, this basically gives you the mean field operator, which we denote as gamma infinity pop here. And we're going to define gamma q as basically the policy evaluation operator, where we try to estimate what are the q functions. And in fact, here is more the soft q functions. And then the policy mirror ascent operator that we introduced earlier, which we denote as gamma, the mirror descent operator, which depends on your step size eta. And the algorithm basically can be viewed as approximately applying some fixed point iteration based on this operator gamma eta, which can be viewed as the composition of just one step of policy evaluation against the mean field and the one step of policy mirror ascent. Right, this is a composition of the mirror descent operator and the Q value estimation or Q policy evaluation operator against basically the mean field here. And it's easy to show that actually the Nash equilibrium of your mean field games is indeed a fixed point to this operator here. And what else we can show is that this operator here, gamma eta, is indeed Lipschitz continuous under the assumptions we make earlier. And particularly, you can see that the Lipschitz constant, of course, depends on kind of what is the regularization parameter rho, and depends on some of the Lipschitz constants of the problem itself, and also the step size eta you choose. And as you can see that if you choose eta, that's this regularization rho large enough and eta large enough, right, you can guarantee that this Lipschitz constant is indeed less than or equal to 1, and this implies that this operator is indeed a contraction. And also for this basically these steps implies that you would be able to converge in a linear rate if you are able to exactly evaluate this. If you are going to compute this policy operator exactly, policy evaluation operator exactly. But we're not able to compute this policy evaluation exactly. We can only estimate it through some TD learning steps. And from the existing work, we know that estimating these Q value functions is equivalent to finding 0 of some operators, or indeed strongly monotone operators F pi here, right? This can be viewed as solving a variation inequality problem. And in particular, there was this algorithm called conditional TD learning algorithm, which has been studied also in Kosalis, Lan, George Lan, and also Lia in 2022, where they introduced the conditional TD learning algorithm, which is basically a modification of TD learning algorithm, where instead of updating your TD, instead of performing the TD update at every iteration using your samples, you're going to just wait several steps in order to collect better samples, right? You're only going to use this last sample you collect when you update the TD learning. So this is just in order to reduce the bias caused by this Markov chain. And the idea here is by doing this, you are able to improve you are able to have better control on your bias, and you're able to achieve better sample complexity. So this is exactly also what we deploy in our subroutine when we solve the when we try to estimate the Q-value functions. And the slight difference compared to the single agent reinforcement learning setting is really that here we don't really have access to the true mean field, right? We cannot really generate sample paths from the underlying Markov chain corresponding to this true mean field mu. Instead, we only have samples from these individual agents, right? They're playing different policies from this one, and so all we have is really just some bias transitions. So, but nonetheless, we're able to show that these distributions or the sample distributions that the agents used is indeed an approximation of the true mean field distribution, right? We can show that indeed the L1 norm among this between the empirical distribution and the true mean field is indeed upper bounded by some terms, which depends on how fast your Markov chain mixes. Depends on what's the number of agents you use, like n, and also depends on what's the deviation between the policy you deploy and the reference policy pi bar. Okay. So this is somewhat also intuitive. And based on this observation, you can then show that with this TD learning algorithm, you can approximately estimate your true Q-value functions that you are really interested in corresponding to the mean field with this error here, which again is similar as before. That depends on the number of agents you use, right? And depends on the deviation of your policy pi from the reference policy pi bar. And as you can see that if all agents play the same policy, then this deviation is going to be equal to 0 for every agent, right? And then this last two terms basically diminishes to 0, and you would only have these first two error bounds. And this basically leads to kind of the earlier conclusion we had that in total, you only need 1/epsilon2 number of samples in the centralized learning setting. Of course, when agents play different policies, which is the case of the independent learning, these last two bias terms will not going to vanish. And then in order to control this error here, you have to use more samples per iteration for the TD learning step in order to compensate for this bias. So that basically summarizes basically how, what are the key results if you just directly run an agent simulator following the policy mirrored ascent algorithm. And this shows that indeed you can efficiently converge to a Nash equilibrium up to the approximation error of order 1/square root of n. And if the number of agents n is very large, then this is basically negligible. And it's worth noting that here we use mean field games more in the analysis to trying to relate these two Nash equilibriums and the dynamics. This is not really used in the algorithm itself. In the algorithm, we don't need to compute best response. We don't need to compute the mean field oracles. We don't need to manipulate our population distribution mu. So there are a number of course, very interesting open questions that we are not able to answer for now, right? The first one being that, can we really relax the regularization condition? Is this really necessary to add regularization to the objective? I mentioned that adding regularization is, or without regularization is harder to show any sort of contraction properties of best response operator, but can we design other algorithms that does not necessarily require contraction properties? This is still seems to be an open question in the field. The other question is, can we combine many of these results with function approximations and to solve much larger scale problems? And this seems to be doable given the extensive success in the single agent settings of combining policy mirror descent with function approximation. So lastly, and also something interesting that we find is there is this discrepancy or difference between the sample complexity between the centralized learning setting and also the independent learning setting, right? It's not clear whether this is really just a fundamental limitation with independent learning, or this is more like a proof artifact. So I think there are also some recent work that shows that in general, for multi-agent systems, independent learning are much harder than having a centralized learning. But it's unclear whether this also is true for midfield games. So with that, I think there are still a lot of things that needs to be done, and I'm happy to take any questions or feedback from you. And I'll just stop it here.
Thank you very much, Niao, for the very nice talk. Are there any questions or comments from the audience?
Hi. Oh, sorry.
Yeah, please go
Can I
ahead.
go? Okay. Hi, Niao. Thank you for the presentation. It was very, very nice. So I had a question about, so you had a slide where you mentioned that the contractivity of the operator is not guaranteed. I think there was one question. There was one slide. So yeah, so I think maybe just a comment. There was, yeah. Right. So I think maybe one comment here is that if you change your best response operator to a softmax, then actually contraction is it holds in general. And I think in the same paper, Shui and Kopel, you can see that if it's a softmax, then it's with the contractivity will hold in general. So I think maybe one.
Right.
Comment
Yeah, I agree with you. Yeah, I think if you consider soft best response, this is more or less very similar to also considering adding the regularization, right, in your objective. Then indeed you can show contraction hold.
Yeah, it's yeah. So for the regularization, you will have to add another extra term to the cost. So that is requiring some sort of assumption on the oracle. But this for the softmax, you don't require assumption on the oracle, and then you will. But again, there's a price to pay. You will land farther away from the mean field equilibrium, which depends. Yeah. So also in the assumptions, if you can move to the assumptions, I had a similar comment about so there was an assumption on regularization.
Okay.
Regularization. Oh yeah. So I think again by using the softmax operator, you don't need any regularization. So you can get rid of the regularization if you use a softmax oracle. So you can basically do away with assumption 3 and have an assumption of just the softmax parameter. And right. And the next.
I think fundamentally, you will anyhow suffer from some bias, right? If you use softmax, there is also the trade-off between, where like the accuracy of the equilibrium that you get versus the convergence speed or the optimization error, right? Here is also similarly, there is going to be also a trade-off here where there is a bias that is introduced by the regularization, and then of course using regularization help you to achieve faster convergence.
Right. But yeah, with the regularization, there is this assumption on the oracle, like the oracle can provide you that regularized cost, which is, I guess, not, yeah. So that's, I think, the same comment. So next slide, I had a comment on the sufficient exploration. Right. I think, so we are going to upload our paper. So basically, you can relax the sufficient exploration assumption by something like a communicating MDP assumption. And under that assumption, communicating MDP, you can basically have a relaxed assumption, but you need something similar to a sufficient exploration. But under communicating MDP assumption, you can prove sufficient exploration assumption. Right. Yeah.
Right. Yeah. I'm sure. Yeah. There are many other different variations one can come up with in order to, of similar flavor that you, and with commuting MDPs, maybe you can then imply that assumption 4 actually hold, or is weaker or stronger than this one, or is weaker. You're saying this simple.
Yeah. That's weaker. Yeah. One more question. Sorry, I think I'm taking a bit more time. So how does the algorithm depend on the n, the number of learners, independent learners? So and how does the convergence result depend on n? So if n is larger, then the convergence is better.
Right. So far, what we see, yes, the larger n is, right, then the better convergence you have. But this is basically the better accuracy you have, but then this does not necessarily affect too much about your sample complexity.
Okay, right.
The sample complexity.
Yeah. Right. Okay. So got it. Right. So okay, earlier on in the slide, I think you mentioned our paper, the Zaman et al. So in that slide, we in that paper we assume that we only have access to one layer. So I guess it's a different maybe setting, right? Yeah. The Zaman and also I think it's we call it a sandbox setting. So so in that setting, it's kind of like you have to report the mean field, right? So it's a different setting, I would say. You have to report the mean field, and there's no way to get, like in your paper, you get the mean field from the n players, whereas in our paper we don't have access to the n players, so we assume access to just one player, and okay. Thanks. I think those are my comments. Very good work. Thank you for your talk. It's very nice work. Thank you.
Thank you. Thanks for the feedback.
Okay, thanks. Yes, Zidai, you have a question, maybe?
Yeah. Hello, Niao. Thanks for your presentation. And I have two questions. Sorry. So first, a question about at the very beginning of the slides, and you said limitation 2, and you said the population won't be manipulated. So can you have a little bit explanation? What does mean the manipulation of population?
Okay, so here I mean that for some of these existing work, some of them would assume, say for instance, you would update your policy, like population distribution, say, with fictitious play, or you would update your population just by mixing your current one with your previous your new update, right? So you need to kind of reset your population new. This is right. By manipulation, I'm just saying like you somehow you are able to control like your mu, and then you're able to just use that mu to generate data as you want.
Okay, so estimation the population distribution cannot be regarded as a manipulation, right?
No, that's a different story. Like estimating is something different. Manipulation here, I'm just saying that you're able to control your mu in a way to control the whole system to generate data and to run your model.
Okay, I see. Thank you. And another question. Sorry, I don't know if I missed something. And so better comparison with centralized learning and independent learning. What's the different input of the both algorithm?
What's the difference in
the input of the algorithm?
The input.
Yeah.
So the input of the algorithm is going to be basically the step size you choose, right? The number of inner steps you use, right? So those are the input, right? There are maybe slight variations on how many number of iterations you run for independent learning setting, but I wouldn't say there are a huge difference between the input parameter inputs, at least. The data input.
Sorry, maybe I didn't clearly say it. So my question is that between the what the difference of the algorithm input, such like the state, the population distributions like this. Yeah.
Okay. So both of algorithms, they would require some initial state that right. So you can use the same initial state distribution basically. Right, and then all this data is going to be generated on the fly as you interact with the system. As the N agents interact with the system, the state, action, reward, all this transition will be generated on the fly. Right, all these algorithms requires just an initial states.
Okay, so the data that will be fitted into the two algorithms are the same.
The data, your input data would be the same, but the data you generated from these two algorithms would be different, right? Because the data that was generated by the centralized version is where every agent is going to play the same policy, right? And then you are going to generate the state action transitions for every agent, right? So in the independent one, agent are going to deploy different policies. So they would have different state action transitions.
Okay, I see. Thank you. Thank you.
All right.
Very clear.
You're welcome. Yeah.
I have another question, sorry. This mixing condition, etc., is related to the fact that and even the strict contraction on the transition is related to the fact that you want to do you want to find the stationary equilibrium. And is it possible to adapt the algorithm to the finite horizon setting, or have you thought about it, or is there like a major difficulty if you take a finite horizon mean field game and you want to compute, the sequence of distributions over a finite number of time steps that represents the Nash equilibrium?
Right, this is a very good question. I have to say we have not thought about how to generalize it for the finite horizon setting, but I would assume these, similar algorithms could also apply there as well. Yeah.
Okay, thank
you. Can I ask a question?
Yeah, sure.
Yeah, thank you, Niao, for the very nice talk. I apologize, I cannot use my camera right now. I just had like a simple, naive question. If you are using this independent algorithm in the situation where you do not have contraction nor monotonicity assumption, are there instances where the return policies actually coincide, even though there is no contraction and no monotonicity? Have you seen some instances in your simulations like that? It's just like a naive question. I'm not sure if it makes sense.
Right. Yeah, this is a good question. I have not run any simulation, so I could not make any conjecture here, but I would assume that it's possible that you don't need this, or for certain games with special structure, maybe they're very specific, such that maybe contraction doesn't hold, maybe you don't have monotonicity in your reward, you can still solve it, or you can still convert to the true Nash equilibrium. I think that's highly likely, and it will be very interesting to try to extract what type of structure exactly that can ensure this, and I think that would be a very interesting problem.
Yeah, thank you. That was exactly the idea that I had behind my mind. Like, if you did the simulations and you saw that in some situations, these return policies in the independent case were actually the same, maybe there is a new structure. But yeah, I thought you were making the simulations. My bad. Thank you.
Thank you, for the question.